Hello friends, we are continuing with the next video, that is video 2 on a series of 20 videos on data science, and today's video is going to be on a topic simple exponential smoothing technique. In video 1 we discussed moving average technique, and today we are going to learn the simple exponential smoothing technique. As you can see on the screen, the green data which is coming from the data set, which is nothing but a raw data, which is looking very fluctuating, and if you want to smoothen this data, you can do it through simple exponential smoothing technique. Then you will see the result would look like what you see in red. So we are going to discuss this technique today. So in the last video, video 1, if you have not seen that, please go back and see that. Still, I will be explaining the summary of video 1 here again. In that we discussed the moving average approach to make the data stationary. For that, we had taken window is equal to 2, moving average window is equal to 2. That means, suppose this is the time series data, every 1 hour we are taken. So for window is equal to 2 means you are grouping these first two data, taking an average and writing down in the second place. Again slide this window again here between 290 and 300. Then average it and write it down in the this place, third place. So you are going on moving window is equal to 2 from left to right and writing down the average. This was the moving average technique. Now in that particular case you can see that since the temperature at 2 p.m. is more recent than that of 1 p.m. For example, you go here, suppose the temperature at 2 p.m. is 330 and 1 p.m. is 310. So in this particular case, you see that actually always in moving average technique, you will see that since you are taking the average of the first two, again next two, like that, so for each input there is an equal weightage given to the next forecast. So that means the weightage is given equal. For let's say window is equal to 2, then equal weightage is given to both. But practically this is not the case. Practically sometimes it may happen that the temperature at 2 p.m. since it is more recent than that of 1 p.m. then why equal weightage has to be given between these two values? Maybe the most recent value should be given more weightage. So that means the next forecast should be dependent on more weight on the latest data. So that is what it is. So this has led to an approach called simple exponential smoothing. So I can explain that concept more clear here. Let's say you have a data set, raw data. Let's say you have 7 points. Between 0 and 1 it is linear, 1 and 2 it's linear, data is increasing linear up to 5. After that from 5 to 6 this is a flattened slope. Then 6 to 7 again it is a linear variation. Now what should be the next? It should follow the linear because it should depend on the latest trend. It is not that next may look like a flat actually. It is not good because it has to more dependent on the latest one. So that is why the simple exponential smoothing technique is used, and this technique is very suitable for forecasting data with no clear trend or seasonal pattern like what you are seeing on the screen. So simple exponential smoothing is now a method that uses is parameter called alpha. I will introduce you alpha, a constant, which is going to decide how much weightage should be given to the most recent observation. So, this can be mathematically expressed like this. The next value, that is yt plus 1 is the next value. The forecast should be alpha times xt. Xt is the current data, and yt is the previous data. Now, this is the next data. This is the previous data, this is the current data. Now, when alpha is equal to 0 or alpha is equal to 1, let's say, what is the effect? Alpha is equal to 1 means this becomes 1 minus alpha becomes 0. So, there is no effect on the previous data. So, the next forecast will be dependent on the current moment data. So, the other way, when alpha is equal to, let's say, 0, the current moment data is not having any importance, and the previous data is having the highest importance. So now alpha varies between 0 and 1. With a higher value of alpha, more weightage is given to the most recent data. As we discussed, higher weightage is given to the higher alpha, will have more weightage given to the recent data, making the smoothing process more responsive to recent changes. So different alpha values result in different levels of smoothing. The optimal value of alpha is determined by the manual tuning based on the requirements of forecasting. Now, alpha has to be varied and you have to come out with the best alpha. So, in order to understand this, you have to, you can practically test a Python program to experiment this. See, as I said before, you have to have pandas library and matplotlib, which is there, going to be in all my videos in the future, to plot the data. And you have to use state models, and you have to import from that library, you have to import simple exponential smoothing. Now, the data set is nothing but a sine wave.csv. It is nothing but an Excel file with one column of data, because it's a time series data. Only one column is there with respect to time or whatever actually. So, this has been already created. You will see in my description this file. You should simply print this out. You will see a series of data, and it is a distorted sine wave which we have created. Now, what I am going to do is I am going to apply simple exponential smoothing on the data set. With the smoothing level is equal to I. I will be varying here in this loop from 1, 2, 3, 4, 5, 6, 7, 8, 9. When I is equal to now 1, what will be the I value? 1 minus, let's say, 1. That means 1 multiplied by 0.1, that is 0.1. 1 minus 0.1, then we become 0.9. In the next iteration, you will see that when I is equal to 2 here, you will see that this becomes 0.8. 1 minus, you see that 2 multiplied by 0.1, that is 1 minus 0.2, that is 0.8. Like that it will vary. So the I will vary from 0.9 to 0.1. That is nothing but our, let's say, the alpha. That I is being passed here, smoothing level, and you see that you are plotting that simple exponential data in this particular case. Now, as you can see on the screen, these are simple lines to plot that. You see that what is the effect of alpha? When alpha is equal to 0.9, it looks like that. And when alpha is equal to, see, 0.8, it looks like this. You see the last trend. And alpha is equal to 0.7, it looks like that. And you see that as you are going away from 1, you see that the data, the last one is going away from the current moment data. Otherwise, you see that it was coming very close. So that means alpha has to be close to 1. That is always forecasting the yt will be more dependent on xt. Xt is nothing but the green line. That is what it shows. Now, what is the effect of this exponential forecasting effect on different alphas? That can be seen more clearly from this example. Let's say there is an exponential smoothing table where the alpha was 0.2. Alpha was 0.2. When alpha was 0.2, let's say the sale was like this and forecast was like this. And sale minus forecast is nothing but the error. And you take the square, error square, in this column, and you add all of them. You can see that you add all of them and divided by the 6. So then what will you get? 11.58. That is called the mean square error. In any machine learning problem, mean square error should be the minimum. That is the best value of alpha, or nothing but in any machine learning problem, the mean square error has to be minimized. So, you can see the effect of alpha from this Excel table. When alpha is equal to 0, as I discussed earlier, the forecast follows yt. There is no effect on xt. So you can say all the data are 135. Initially, see, this is actually, but now when alpha is equal to 1, next forecast just simply follows xt. See, 134 here, 134 here, 143 here, 143 here. It simply follows. This is the xt. This is yt at alpha is equal to 0.3, 0.8, alpha is equal to 0, alpha is equal to 1. So what is the effect of alpha is equal to 0? So there is no effect on xt at all. It is simply projecting yt values, previous values. Whereas here there is no effect on yt, it simply follows xt. This is as per this equation which we discussed earlier. Alpha is equal to 1. That will be the ideal situation we are looking for. It should follow xt. From this table it is very, very clear. Now the summary is the program demonstrates simple exponential smoothing a time series dataset, that is sinewave.csv, for various smoothing levels. Now you will have more such videos, and also program is given in the description. However, I will be just demonstrating the program which we have just seen in my video. This is a program, just the way you just run it on a standalone Python in your PC also can be seen in the description, and all the helps are given there. You can simply recreate this very easily. When I run this program, you can see that now how it is going to run. See, I am running this program. When I run this program, this PC is a bit slow. Because of that, I am not able to run this. However, I think I will be able to do this. Please excuse me for this delay. Now you are just running this program. You can see that actually it's running for different values of alpha. What will be the effect on the output, which we have already seen in the video, but however in this program it will be more clearer to you. See that this is for alpha is equal to 0.1. It looks like that. Now alpha is equal to 0.2, it looks like that. So now alpha is equal to 0.3. It is coming close to xt. You see that? More and more alpha close to 1 means it will come close to xt. Xt is nothing but the green line. See that next one for alpha is equal to 0.4, it looks like that. So like that you can see that when alpha is equal to 0.7, so it is becoming more close to xt. So that means it is ignoring yt much, but it is becoming more close to xt. That means the weightage is given to the most recent data. That is what it shows. And 0.9 is, see that it's exactly trying to follow this also, and also it smoothens also. Okay, see you in the next video.